Good morning. So I don't have much announcements, I think. It's just a quiz. The deadline is this Thursday. That's pretty much it. Let's jump into the lectures. Okay, so hopefully we're going to finish talking about multiprocessors and start talking about real-time systems today. So so far we've seen different architecture choices when it comes to multiprocessors and their implications, mainly about caches so far. And today we'll talk a little bit about non-uniform memory accesses and their implications for multiprocessors. So let's dive into scheduling problem in multiprocessors. Okay, so I kind of spoiled it by that slide sitting there. Okay, so one option is right off the bat, we have had like a ready queue, which is basically what you're doing for your labs. So you have a ready queue, and in a uniprocessor, there's only one CPU that would basically take tasks from this ready queue. In a multiprocessor, a naive way to just extend this is to make every processor be able to extract tasks from this single ready queue. So what would be the problem with this? So you can see that this becomes a single bottleneck of your system. If you have a single ready queue that every CPU is basically using to schedule tasks, then that single queue becomes the bottleneck of your system. Now, you definitely will have to protect this queue with mutexes and locks, because it's a shared object every processor is accessing. And everything that we talked about, lock contention, becomes valid with this. And here is a single entity in your system that you really don't want to waste time on. You want your scheduling to be as efficient as possible. Now, if you share it between different cores and have to protect it with mutexes and stuff, then you can see how bad it could be for your system's performance. The other problem with this, so that's the first problem. The second problem that with this is you won't have much cache reuse for each task. Why? Let's say task 1 runs on CPU 1 and then goes for I/O. Once it comes back from I/O, you will add it back to the ready list. Now, next time T1 is on the front, it could be dispatched by any of the other processors. So it could go to CPU 1 or it could go to CPU 3 this time. And whatever T1 has cached here, let's say it just cached a lot of stuff and it came back. Let's say the system is actually empty. There is no other tasks in the system. So T1 goes to CPU 1, runs, caches some data, and then comes back. And by chance, next time CPU 3 dispatches T1 or dequeues T1 and starts running it. So now T1 is running on CPU 3. It has to cache all its data again, because there is no guarantee that it's going to go back to the same CPU that it started with. So you would get a really limited cache reuse, and that could have performance implications as well. So how do we fix this? Well, one easy fix is to put multiple queues per CPU. So now each CPU has its own queue. There's no sharing between different CPUs and a single queue. Now, do you notice any problem here? it's actually very much obvious if you look at this and scratch your head a little bit. You'll realize that, okay, you could get into situations where one CPU is overloaded and one CPU has nothing to do. And you can easily see, I'm going to just now connect dots with the lecture from a week ago, where I said that the single invariant that we want, the single goal of a scheduling is if you have CPU cycles available and you have tasks to run, ready tasks, then run them, right? That was a single easy thing to say, at least. And you can see that that single goal or invariant is disregarded here. Now CPU2 is empty, but there are tasks waiting on CPU1 and CPU4's queues, whereas they could have just ran here. Okay, so load balancing is one major issue. The second issue is with priorities. Now, let's say you have a load balance system. Let's say all of your queues have 2 tasks. But let's say one of the CPU1 is running high priority tasks, whereas CPU2, 3, and 4, they are running low priority tasks. So what is happening here, if let's say all of them have 2 tasks in their queues, CPU1, because it's running 2 high priority tasks, basically those 2 high priority tasks will compete with each other. So each one of them will get half of the time on that CPU. So each one of them gets half. And so does any other task in CPU2, CPU3, and CPU4. So in essence, you are treating all your tasks equally, right? T1 gets the same amount of CPU than T2, than T3, 4, 5, 6, 7, and 8, right? All of them will get the same amount of CPU. And that's against what you wanted. That was the whole idea of having priority. You wanted the high priority tasks to get more CPU time than low priority tasks. So you can see here that this would basically go against that goal. Okay, so how do we fix this? We can actually fix both of the problems by load balancing. And we need to also, so this load balancing 2 words, we have to do both of them. So we have to define load. So when we define load, we probably want to consider the priority as well. So we want somehow, if CPU1 is running 2 high priority tasks and CPU2 is running 2 low priority tasks, we want each high priority task to have a higher load, or pretend that it has a higher load, so that if CPU1 has 2 high priority and CPU2 has 2 low priority, your system shouldn't be load balanced, right? Although both of them are running 2 tasks, but because of the priorities, if we somehow integrate those priorities in the definition of load, then your system is not load balanced, because CPU1 has more load than CPU2. Then you would want to load balance, and then that change hopefully makes sure that high priority tasks get more CPU time. We'll see how that happens. So we have to redefine load. We also have to come up with some mechanism to balance the load between the CPUs. Okay, so first let's focus on the first one, which is how do we define load? How do we track? What metrics should we use for load? So option 1 is to just take care of the number of threads or number of tasks, which is basically what I just described. And you should by now know that this is not going to work because of what you can see. So low priority threads could get the same amount of CPU time as high priority ones, which is what we discussed. So option 1 out of consideration. What is option 2? Maybe when we define load, we should also consider threads weights as well. So let's say, here's an example. Let's say one queue has 1 thread with weight 9, and another one has 9 threads with weight 1. So maybe we should, multiply weight by number of threads. So the load on this CPU becomes 9. And do the same thing here, 9 threads, weight 1, that's also 9. So seems like we have a load balanced system. Both CPUs have load 9. If we define the load to be number of threads times their weight, or the sum of the weights, that's better. So sum of weights on each CPU. Now the system is load balanced, but is this good? Does this achieve what we want? And the answer is not really. It's better than the first option, but it's not perfect. Why? Let's say that this high priority task that you have often sleeps, right? Does some CPU. It's an interactive task. It does some CPU, and then it goes to a long I/O stretch. What happens? So what happens is, well, in the time that this guy is doing I/O, then the CPU is idle, right? And the other CPU is just running those 9 tasks. So maybe, I mean, we will talk about this as work stealing stuff, but then CPU 1 might feel like, okay, I'm idle. I'm gonna get some of the tasks from CPU 2 to run. Maybe I migrate them and I start running them. And as you can see, the moment this task comes back from I/O, you have to again ship those tasks back to CPU 2, and now you're back to running 1 thread on this, 9 threads there. Then this guy goes to I/O, then you have to again migrate some tasks to CPU 1, then comes back, you migrate them back. So you can see that frequently you're migrating tasks between the 2 CPUs, and that's bad. So that brings us to option 3, which, by the way, is the way that it's been done right now in Linux's completely fair scheduling policy. So the way it's done is a combination of threads weights and how much they use CPU. So we don't really care about your weight if you're not using CPU by much. So basically, it's kind of like a multiplication of your weight times how much you're utilizing the CPU. And if you do that, then you address the problem that was raised here. So you will have a load balanced system that you don't need to migrate tasks between the CPUs. I'm not going to go deeper than this, but it should give you some sense, right? So if you have this thread, thread with weight 9, if it is utilizing only like 50% of the CPU over time, then we want to lower its load to 4.5. So we shouldn't be looking at it as a load 9. We should be looking at it as load 4.5, because half of the time it's not using the CPU, so it shouldn't have a weight for the time that it's not using the CPU. And by doing that, you sort of have a metric now that makes sense, and now you can think about how you can balance the load. So this is the option, as I said, that is being used in Linux. One thing that you have to consider is how do we deal with threads, with processes with a lot of threads versus processes with 1 or 2 threads. So do you want to distinguish between the two? Right now, I think, I'm not 100% sure, but I think the way that it's working in Linux is process, not thread. So we define weights for processes. We don't define weights for threads unless explicitly done by the programmer, I think, or by the user. So by default, you give weights to processes. Now, if one process creates thousands of threads, then you divide the weight between all the threads. So sum of the weights of all the threads should become the weight of the process. So basically you divide it. So you're fair between processes. You're not doing it between threads. Because otherwise, everybody would have incentives to create thousands and thousands of threads to take more CPU if we were to do it on thread basis rather than process basis. So, and it's kind of done with auto grouping feature of Linux. So for each group, you define weights, and then if a thread creates, if a process creates threads, all of the threads would join the same group, and they would all share the weight of that group. So it would get divided between them. Okay, so we're done with defining the load. Now let's talk about load balancing. You might think, okay, if I have a notion of load, what the load means, then it should be simple to just balance it, like make it equal over all the CPUs. And actually this was what was a common sense back then in 2001 when we started having multiprocessors. So this is a quote from Linus. So he said that, so if you don't know the guy is the father of Linux. So he created Linux. He said, this is like beginning of multiprocessor era, where we started going from systems with a single processor to systems with multiple processors. So he said, I suspect that making the scheduler use per CPU queues together with some inter-CPU load balancing logic is probably trivial. Perhaps already exists. And I don't feel that people can screw up the few hundred lines of code too badly. So he was saying that, okay, we have a good scheduler for a uniprocessor. Now we are moving to a multiprocessor. It shouldn't be that hard, and we shouldn't be messing it up. I got a question I will answer after this slide. So let's see how that went. So this was actually a good common sense back in 2001, because even if you had a multiprocessor at that time, that multiprocessor had at most 2 or at most 4 CPUs. So that was the highest number of CPUs, like quad-core CPU probably at that time. And for those systems, it's probably not that hard to do load balancing. You only have 4 cores. Today, I actually bought like this December. I bought AMD servers, and if I'm not mistaken, each CPU that we bought had 128 cores, physical cores, which amounts to 256 virtual core. I mean, vCPUs. So, and this is actually just increasing. So nowadays we're talking about hundreds of cores. It's not anymore. We're not talking about 1 or 2 anymore. We're talking about hundreds of cores, and that could make things a little bit more involved than what people thought in 2001. The reality of it is, because of all the other stuff that we have done for performance of our multiprocessors, particularly with the notion of caches and the memory hierarchy and the non-uniform memory accesses, load balancing has become an expensive process just to migrate tasks between your CPUs and make your CPU to be a your system to be a load balanced system. This process, as we will see some of its aspects, is an expensive process. You could imagine why, right? If I'm running my code on one CPU, and for whatever reason I have to migrate this code to another CPU to make my system load balanced, what does it even mean? It basically means you need to migrate all the data first of all. So let's say you have caches here, you were using your local memory here, and now that the code is going to run on a separate CPU, you probably will have to, warm up the cache, meaning that you have to start accessing from scratch to cache your data back. You probably don't want your CPU to access remote memory a lot, so you might actually want to migrate data to the local memory so that you access local data. You also need to take care of the operating system data structures because your task was in one CPU ready queue. Now the TCB, all the data structures that kernel holds for that CPU also needs to be migrated to this CPU. When I say migrated, we're talking about memory locations, right? So basically either warming up the cache or moving the data from the remote memory to the local memory, or taking the bullet and just accessing remote memory for all the memory accesses, which is not cool. So anyways, it's costly just to do the load back to migrate a task, let alone, I mean, add to that, who's gonna calculate the load? I mean, you saw that like just the metric that we defined for load was like multiplication of CPU usage time times the weight. Now you have to do that for all CPUs, for all the threads that are running on that CPU, and then you have to have an algorithm that looks at the load on each CPU and decides, okay, I want the load to be moved from this CPU to another CPU. This is a kind of like a mathematical optimization problem, right? Calculating the load and deciding which task has to migrate, which task has to stay. So all of this is like, okay, load balancing is costly. And we might want to do it if you have a small system, but if you have 128 cores or more, how are you going to do that? Like, how frequently do you want to calculate the load? How frequently do you want to migrate your tasks? Given the overhead, if you go back to when we were talking about uniprocessor scheduling, I told you that calculate your overhead, your context switching overhead, and set your time quantum to be 100 times more than that overhead. Now, if you look at this overhead of load balancing, you don't want to do it that frequently. You should set the frequency to make this overhead really only 1% of the time that you're doing it. So long story short, this led to a lot of optimizations in Linux kernel. So instead of doing it really frequently, instead of doing it per core, they started like just cutting it off. Maybe we shouldn't do it frequently. Maybe we shouldn't do it per core. Maybe we should group cores and then calculate the load between groups and so on and so forth. Again, long story short, we ended up with a something that is very commonly used called work stealing, which basically means don't bother about load balancing until one of your CPUs becomes idle. The moment your CPU becomes idle, start panicking to maybe you should migrate some task on this CPU. And then the CPU that gets idle will look at other CPUs, see if they are overloaded. And if they are overloaded and the cost of bringing a task to run or migrating a task is less than the time for that task to stay in that queue and be executed normally, then migrate. So basically, we postponed load balancing so much so that we get to an emergency situation where one core is now idle, and then we start doing the load balancing. So this is what happened in reality. So let me answer some of the questions. Would processes be in the ready queue in option 3, or would it still be threads? What does that mean? Would processes be in ready queue? Yes. So if you're asking about how do we, what processes do we care when we are calculating the load, you really want to focus on ready to run processes and basically runnable processes when we're calculating the load. Now, if I'm not mistaken, I might be wrong, and there might be different types of a scheduling policies. But let's say your process has weight 9, and it creates 9 threads. So each thread should share that 9 weights. So each one of them gets weight 1. Now, if 8 of them are sleeping and only one of them is active, you still treat that one by weight 1. You don't migrate the weight of the sleeping threads to this thread. That's as far as I understand it. There might be different policies. There might be. This is an area that anybody has their own opinion. There are so many different scheduling policies. You could do so many different things. One could actually study which one is better. But as far as I know, you don't move the weight of sleeping threads to active threads, if that was the question, I think. The other question, sorry if it's slightly off topic, but is there any way to enforce a hard upper limit on the response time for all tasks in a system? I'm thinking of like medical devices or safety sensors or on cars. So we sort of answered that question in the lecture we had with uniprocessors. If you remember, we had this target latency or target response time that you define. You say my target response time is 20 milliseconds. What does that mean? It means that I want any task in my system to run at least once every 20 milliseconds. That's target latency. And then if you have, let's say, 10 tasks in the system, then you divide that 20 by 10 to get 2 to set your time quantum. So you basically adjust your time quantum. But then the limitation of that was that we had to put a minimum response time, because if you have hundreds and thousands of threads, then it's not reasonable to divide your target by that much, because then it would interfere with the overhead. So the way it's done in real-time systems that you're asking, right? And we'll talk actually about it, is differently. So just wait a little bit. If you don't get an answer when we talk about real-time systems, how we can do that there, then ask this question again. But so far, the mechanism that we have seen is just setting a target latency with a minimum quantum size. So another question, could you clarify the weighting thread in the context of processes? I thought that a process with weight 9 that creates 9 thread would create each thread with weight 9. Is that correct? No, that's not correct. So exactly the opposite. So if the process has weight 9 and it creates 9 threads, each thread gets weight 1. You want the sum of the weights of your threads to be equal to your process's weight, because otherwise a thread could create thousands of threads to basically increase its weight, to double its weight every time it creates a new thread. And that's pretty much what we don't want to allow. So they share the weight, meaning that they each one of them will get a share of that weight. Okay, so let's move on. So I think I made my case about what the state of the art is in terms of work stealing and load balancing. Now, there are still few questions that you need to answer about processor affinity. So what is processor and affinity after all? So it means that where does the thread, where does it belong to? That's the affinity of a thread. So when a thread runs on a processor, the cache content of that processor will store the memory accesses of that particular thread that is running, right? And we call that affinity of that thread. Basically, it's as if like that thread has a home, and that the home of this thread is this CPU. Now, when we migrate someone from its home to some other CPU to have a new home. And then, as I mentioned, it would have performance costs, it would have all sorts of costs and waiting time for this migration to happen. Now, you can enforce some sort of affinity. You could tell your operating system that I want my thread to only run on these processors. That would be setting affinity. Now, setting affinity could be soft or hard. So if you have a soft affinity, you tell the operating system that please keep them there as far as possible, as long as it's possible. But then you don't press hard. You don't say that, oh, no matter what, it should run there. You don't say that. And then operating system will try its best to run your thread on those cores. And if not possible, then operating system might migrate your task. So there is no guarantee that your tasks, after all, will run on those threads. You could also have hard affinity. You could just bind your thread to particular CPUs and say, no matter what, I'm okay if I wait for 2 days, even if there are CPUs available somewhere else, don't move my task. And that would be a hard affinity. Both of them are available, actually, as far as I know, in CPU, in Linux. You can set CPU, you can use CPU set, C groups to set affinity of your threads. Now, why did we talk about those? Well, here is a modern architecture. This is an EPYC AMD processor. If I'm not mistaken, yeah, I think the system I bought is very close to this one. So I'm not going to walk you through exactly what this means, but just to give you like overview of what this actually means. So each one of these groups that you see here, each one of these boxes has some number of cores. I think 4 or 8 cores reside in each one of these boxes. And then they have their local memory, as you can see, these yellow cylinders here. These are the local memories for all the CPUs that are in this box. This is their local memory. Now, if a CPU here, if a thread that is running here needs to access data that resides on these memory blocks, and then it has to go through this network interconnect or whatever interconnect that is to go to this and then access memory here. Or if the memory resides here, the data resides here, then the request has to go through through one of these to get here and be answered. Now, there are different distances that you could, like as I mentioned, accessing memory here requires you to go one hop from this group to this group to get your data. Whereas going from here to here requires a long hub to access this CPU. So the way we do this in operating systems, as I said, we want to minimize how much we are doing load balancing. We don't want to do load balancing per cores. We probably want to group processors together and then compare their loads. So the way actually it's done is we group CPUs that have similar or uniform memory accesses together. We call this NUMA 1. And then we put every other CPU that is one hub away from this group to be on NUMA 2. So NUMA is what we saw, the non-uniform memory access. So all of the CPUs here have a uniform CPU access on their local memory. But then if they want to access any of these memories, then they have to go one hub away. So all of these groups become NUMA 2 with regard to a CPU here. And then all of these guys become NUMA 3 because they're 2 hubs away, right? And then we can actually migrate we can, if there is a load imbalance, we can actually calculate the load of this NUMA node, and then this NUMA node, and then this NUMA node. And if you feel like you can migrate to this guys, you prefer to migrate here because the cost of migration is lower. It's just one hub away. And if these guys are also busy and you have to migrate it here, then this is your last resort. Now, people have tried in new architectures to reduce these numbers, different NUMA nodes. So in the new architectures that at least AMD is putting out, they only have 2 NUMA nodes. So they have this uniform bus here between all the nodes so that they all have uniform access to their memory, so that we have all of them in one hub, one NUMA node, and then this becomes the second NUMA node. So one thing to note here is that so this NUMA 1, NUMA 2, and NUMA 3 are all with regard to a core in this box. If I care about a processor in this box, then this guy becomes NUMA 1, these 3 become NUMA 2, and this becomes NUMA 3. If I care about a CPU here, then this guy becomes NUMA 1, these 3 become a NUMA 2, and these 4 become NUMA 3, right? So it's the way you're grouping them depends on who are you thinking about, which particular core you're focusing on, because everything is relative to that core. So that's basically what happens in Linux, sort of. Cores are divided into NUMA nodes, and then you try to load balance between NUMA groups. And then if you are to migrate, you prefer NUMA nodes that are closer to you than the ones that are further from you, which makes sense. So you have this hierarchy of scheduling domains that you could migrate your task between. And when you do load balancing, you basically want to load balance between these domains rather than any 2 cores. You want to, it's better to do it per core, but then it costs a lot in a system with 128. Then you have a choice of 2 from 128, which is a lot of different choices. Whereas if you just look at the NUMA nodes, it's much less. If you group the CPUs to domains, that reduces it very dramatically. That probably this brings us to a question. Let's say, I can load balance running tasks. What should I do with new tasks that are created, or the new tasks that are coming back from I/O? What should I do with them? So generally speaking, what the operating systems do, if you create a task, at least as far as I know in Linux, this is what has been done. If you create a new task, that task gets the affinity of its parent. So wherever the parent was running will be the home of the new child. We'll see how this could be actually a problem. What about threads that were blocked or were on I/O and now they come back? Where do they go? So one naive way of doing it is, well, put them back where they come from. So where they ran last time becomes their home. That's one way. But here is the problem. What if that CPU that was the home of this thread is overloaded? By just putting them back to where their parents were, or where they ran last time, we're missing an opportunity of exploring other cores that are empty, because this is like a new thread. I can put it anywhere I want, sort of. So that's actually bring us to one strategy. One strategy that you could do is, when you have a new thread, you can look at other CPUs. If you find a CPU that is idle, that is completely idle, and you actually care about this being idle for a long time, not just for the past, hundreds of, for the past 10 nanosecond or millisecond, because you could get these situations where you have a bunch of threads. Let's say you have a CPU that is running 10 or 20 threads, then they all go for I/O. The CPU gets idle for a little bit, and then they all come back from I/O, and then they go for I/O, they come back. So if you have this situation, then your CPU could be idle for a short amount of time in between when they go for I/O and they come back, and you actually shouldn't consider this CPU as idle, although it is idle for some number of times, but you have some recursion happening here. So you want to find a CPU that is idle for a long time, and then if there exists such a CPU, then instead of putting the new thread or a thread that woke up back where it came from, you could actually put it on the new CPU. Okay, so this should be it. What I'm going to talk about. I mean, that's pretty much what I had about load balancing. I think the takeaway is, first of all, it's sort of an open problem. Really, like I actually should have mentioned this paper back here. Yeah, where I talked about. So this paper, do I have it? No. Probably will come later. Let me see if I have it. Yeah, I think it's here. Assign. Okay. Yeah, I had it in the first lecture on scheduling. So this is a paper from 2006. You can find the link on my website. I really recommend, if there is only one optional reading that you want to do for this course, read this paper. It's an easy read. There is not much, if any, math in it. And it talks very well about multiprocessor scheduling. It's the paper is a decade of wasted cycles, or if I'm not mistaken, on the course website. Definitely check it out if you have time. Yeah, this one. the Linux scheduler, A Decade of Wasted Cores. This is actually from 2016. I said 2006. 2016. It's a recent paper, relatively. I really recommend anybody who is interested. If you want to do one optional reading, make it to be this one. And it's a super interesting paper, and it talks about exactly how we thought that scheduling a multiprocessor is easy, and then we did all these heuristics that I just talked about, where we put a new thread, how do we load balance, when do we load balance, and all these ad hoc and heuristic decisions that were made from 2001-ish till now led to so many bugs in the Linux scheduler. So much so that they figured that there are tasks that are slowed down by more than a factor of 100 times, which is mind-blowing, really. So definitely look it up. So the scheduling policy for the scheduling of multiprocessors is, in my opinion, is not a solved problem. It's still done heuristically, because doing it exactly would require a lot of time. So now the question is, which heuristic is better than the other ones? And then there are so many aspects of it that you have to, what is the load? How do you load balance? So I just laid out some of the basics, but then as the questions came up, you saw that it's really flexible, because we're in a land of, ad hoc decisions. So this is one area that I think is interesting to see what happens coming next. One more thing to mention is that we're actually transitioning to another interesting era in operating system scheduling, and that's again due to the trend in software and hardware. So right now, the trend in software is basically we're dealing with a lot of data, we're dealing with machine learning applications, and the trend in hardware is that we're creating a lot of specialized hardware. GPUs were the first ones, FPGAs. Now you have machine learning cards, you have tensor processors, you have all sorts of specialized hardware that are being now added to the system. And it's sort of the job of the operating system. Right now, I think by looking at the landscape, many of the management and scheduling policies are being done by, again, ad hoc ways of each company creating their own, software stack and scheduling their tasks differently. At some point, we probably will unify this. We'll have, that's what I think will happen. We'll have support in the operating system for different specialized hardware. So it's kind of like now we're in a new era. If we were at the beginning of the multiprocessor era in 2003, 2005, now we are in the operating system field. We're in the era of transitioning from multiprocessors to specialized hardware. So that's where we are right now. Now, the last topic I wanted to cover is energy efficiency. I mentioned at the beginning about asymmetric processors, where we really might not always need high performance cores in our system. Maybe we have applications that don't need high performance. They're doing a lot of I/O maybe. So we add low power cores into our system. Now we have a heterogeneous asymmetric processor to manage. This is good for a number of reasons. One, we still can manage and meet performance targets because we have high performance cores and then low performance cores. If you have an application that needs a lot of performance, well, you have a high performance processor. If you have an application that doesn't need it, you can actually achieve energy efficiency by running it on a low performance and low power processor. Now, this is good theoretically. Now, how do you manage the system? Again, you have to think about, okay, migrating tasks between the two, deciding whether or not your application needs high performance CPU or not. So I think some of the systems actually put this decision to the programmer. So you can actually say that run this portion of my code on a high performance and run this portion on low performance. Operating system could send signals saying that, okay, I'm going to move you to a low performance, or I'm going to move you to a high performance, or, you know, maybe a hybrid model where operating system gives some signals and the application gives some signals, and then they make a decision. So I think what I have here is, yeah, we talked about this. So the reason we have asymmetric processors is because we want to maximize performance per watt, because watt is now important to us, right? If you have a cell phone, if you have a watch, you don't want it to burn the hand of the user, so you care about how much performance you get out of each watt. And if you want to maximize performance per watt, that basically means minimizing energy per instruction. Now, you can now decide if you want to run this particular instruction on this CPU, or you want to run it on this other CPU. Now, some of the things that you need to care about is the capacity of each one of the CPUs, how much capable they are, what's the relative capability of your high performance CPU to low performance CPU or low power. Usually it's done by the frequency, usually, not always, right? Because it could also have other factors into it. So you could have multiple lanes, for instance. It's a super scalar. So it's not just the frequency, it's also some other capabilities that your high performance processor could have compared to the low power one. So you kind of like identify how much powerful your high performance is compared to your low power. And then you probably need also an energy model, basically, because you want to minimize energy per instruction. So you have to have some notion of a model that tells you, if you run this instruction on this CPU, this is how much you're going to consume power. If you run it on this CPU, this is how much you're going to consume. And then given that model and given the difference in capabilities of your processor, then the operating system can make a decision. Actually, this module is available, EAS module is available in Linux, I think. I'm sure. So it's an open source, you can actually look it up. And it does some heuristic and some optimizations to do the load balancing for you. Okay. Yeah, so some of the things that you could potentially do is, when, like we talked about thread affinity and what happens if a new thread comes, then you can, instead of just putting it on a processor with the lowest load, you could put it on a processor with the lowest energy consumption without hurting your performance. That's one thing that you could do. Okay, so this is a side. I'm not actually going to put much time on this. This is all available on the internet. You can look it up. We started with Linux with ON scheduler. So this was from version 2.4 to version 2.6. So for that period of time, we had ON scheduler. It was not the best scheduler that you could have, and it actually started showing low performance as we started having multiple threads. So managing threads was hard for this scheduler. So it was designed for single-threaded processes, but was not doing well with multi-threaded applications. So that's when, around 2003, the scheduler changed to O1 scheduler. So if you remember, we talked about predicting behavior of applications. So that's where O1 scheduler put a lot of effort in and actually failed. So it wanted to give more CPU to interactive applications, so it started doing some heuristic and ad hoc predictions to predict and classify applications between interactive and non-interactive, and based on that prediction, it started giving more CPU to the ones that it predicted that are interactive. And because this prediction was not good enough, or I don't even know if you can make it perfect ever, so it started making wrong decisions. That's where people thought that it's actually unfriendly to interactive and audio applications. They started trying to solve this by adding a lot of patches to fix it, especially after the architecture moved to NUMA and SMT, but then they exacerbated the problem. So people started thinking about a new one. They came around 2007. Linux kernel moved from 01 to completely fair scheduler. So the power or the strength of 01 was its low scheduling complexity, which was 01 scheduling complexity. It had really low scheduling complexity, and it's a strength. So with completely fair scheduler, we sacrificed this 01 with O log n, which is probably what most of you, I hope, implemented for lab 2. So that's what we sacrificed, but it achieved fairness, which was important at that time, and got rid of all the heuristics that were made in 01, made a better fairness, better investment in fairness by sacrificing the complexity. And so far, it has been completely fair. It hasn't changed ever since. There has been actually many new scheduling policies. This brain fuck scheduler is one of them. The idea for this was that there was this guy who is very famous in Linux community. He was not very happy with completely fair scheduler, how complex the scheduling policy has become. So he moved to a very simple scheduling policy with a single queue for all the CPUs. He basically, I think, wanted a clean slate. He wanted to start from a clean slate in terms of scheduling, without any all the history that was attached to this completely fair scheduling. It didn't work well, I think, moving to only one. It was a simple one. Actually, many people used it. Many people are using it even now. He later on moved to multi-queue skip list scheduler, which is a version of this brain focus scheduler with multiple queues. But it never actually found its way to mainstream. And he mentioned, he wrote an article or a blog post, and mentioned that I never designed it to become a mainstream. I just wanted to do it for whomever needs it, or just an experiment or whatever. But that's something. I think this multi-queue skip list scheduler is also used right now in some systems. Okay, now we're kind of done with scheduling in multiprocessors. The last topic that I want to talk about is let's focus on multi-threaded applications and see if we need to do anything differently for them. So do we need to care about threads, or can we just look at them as units of work and ignore the dependencies between threads? So far, so we started with uniprocessor, then we moved to multiprocessor. I never talked about the dependencies between threads. I always looked at them as units of work that we can migrate from one thread to another thread, sorry, from one processor to another processor, and it's kind of fine defining load and stuff. But is it that simple when it comes to multi-threaded applications? The answer is actually no. So far, we talked about oblivious scheduling. Oblivious scheduling meaning that we didn't care about the dependencies between threads. We treated them as units of work that are independent, and I can do whatever I want. I can run them whenever I want, as long as they're ready. Is that so? And the answer is actually no. So in an oblivious scheduling, we just treat threads independently and we schedule them. It's actually not efficient way of doing it. Why? Because we have, when threads have dependencies and we ignore those dependencies, we could end up paying high costs. So to recognize those costs, I need to talk about what kinds of dependencies threads could have. So that brings us to a different question. What kinds of different parallelism do we have in software? Because that identifies the dependencies that tasks might have. One very famous one that is pretty much used everywhere is data parallelism. The idea is you have big data that you want to do computation on. Your computation is kind of fixed, and you do the same computation on each piece of data. If that's the case, what you could do to parallelize this is to divide your data into smaller pieces and then run this single fixed computation on each one of these data. And now if you have multiple cores, you can put your data, you can distribute your data between the cores and then launch your threads. And then those threads would do work on that data in parallel. The catch here is that it's usually parallel, but at some point, you need the threads to communicate. Like if you know MapReduce, for example, or if you know any other data parallel computing framework, you have these reduce phases where you have these map phases or fan out phases where your threads can run in parallel on different data. But at some point, they need to communicate back. Let's say you're doing neural network application. You train your model on your own data, and now you want to put weights together because each one of them has, like you're in a backprop phase. You want to backpropagate your errors, so you need to now somehow communicate these derivatives that are going to be backpropagated between the two data batches that you had. So you need communication now, right? So it's not always parallel. At some point, you need to communicate between your threads. So this is usually how it works, right? Let's say you have divided your data between your CPUs, they run, and then at some point they synchronize. It could be like they pass their weights, they communicate their weights, it's all reduce or whatever you name it, and then they start again. So what happens if this is your parallelism model and you treat these three as independent threads? What could happen? Here is what could happen. This CPU3 doesn't know that this P1.3, so this is thread 1 of processor 1, this is thread 2 of processor 1, and this is thread 3 of processor 1. If CPU3 doesn't know or doesn't care about dependencies, it could potentially context switch here between P13 to P2X, some thread from P2. Who cares, right? I don't, this in particular, I don't have anything, any hints that this is a bad decision. If I'm CPU 3 and I look at my threads locally and I don't know the dependencies, I might make this decision. But if I make this decision, because all the other ones depend on the result of this P13, this decision basically slows down every single CPU in my system, because now they also have to wait for this synchronization to happen. So this is one example that this oblivious scheduling could cost us. Another multi-threading paradigm or parallelism paradigm is a producer-consumer model, where it's very close to what I talked about the web server, if you remember, and the architecture we talked about, that each thread produces data for the next thread, and the next thread consumes that data, produces another data for another thread. So in this way, the dependency between threads are shown in this graph. As you can see, thread 1 produces for thread 2 produces for thread 3. Now, if these CPUs, each one of them, is oblivious about these dependencies, then it could arbitrarily, context switch between thread 1 and another thread in the system. And by doing so, it basically introduces a delay to all the threads that are running on the other CPUs. So how do we fix that? One of the fixes, this is mostly theory. I don't exactly know if any scheduling policy has implemented any of these ideas. I don't know. I don't think so. Most of the systems that I know still go with oblivious, because the moment you start bringing in those dependencies, the scheduling was already hard. It becomes exponentially harder. But let's say you want to address it. One way of doing it is with doing gang scheduling. Basically, what it means is you sort of synchronize all your CPUs. You sort of make them all be aware that this is a turn that we're going to give to process 1. Let's run any thread that you have for process 1. Then let's run every thread that we have for process 2. Then let's run every thread we have on process 3. So this actually avoids those unnecessary delays that CPUs could introduce if they didn't know the dependencies. But it also has costs. One cost you can see here. Maybe not all CPUs have threads from process 3. Maybe there are short tasks and long tasks. Maybe we're wasting some time here. We could have done it differently. So this addresses some of the issues, but then it introduces some other issues. The one that probably is closest to be implemented, and probably someone could have done it now. People usually do this by hand. If you have written anything for data centers, you usually actually do this by hand. When you launch your application, you just give your application to a set of CPUs. When I was talking about hard affinity, this is one of the use cases for that. So it's called a space sharing. You basically reserve a bunch of CPUs for your application, for your process, and you just bind them. You do a hard affinity definition. So you bind all your all your threads to a set of CPUs, and then you bind other CPUs to other threads, and so on and so forth. So you sort of divide your CPUs. It's a space sharing between your processes. And now all these CPUs are running the same threads from the same process. So they're not going to context switch between the thread from one process and a thread from another process and slow it down. So it's better you're dealing with that, and hopefully as long as your process has threads to make these processors busy, it should work. Now the question is, okay, if I'm going to use this, how many CPUs should I give my application? Now, it would depend on your parallelism model. It would depend on your software. What you probably wish for is something linear. So in this graph, what I have is number of CPUs that are given to each parallel application and the performance on y-axis of that application. So you wish for something linear, meaning that as I give more CPUs to my application, its performance should increase linearly. Usually what happens is you have this diminishing returns. So you have this concave function instead of linear function. So giving one extra CPU doesn't make your application speed up linearly. The returns that you're getting from extra CPUs is diminishing. And more real cases are this limited parallelism. So you get some boost up to a point and then it flats out. So if you start giving more and more CPUs, you don't get any return from your investment. So it's either of these. So this graph shows you that you need to study your application, see which one of the cases you are. And if you are diminishing, what is exactly your curve, how much you should get. Now there are things that you can use to guide this search. So for instance, Amdahl's law is one that you could use. It's actually sometimes it's misunderstood in operating systems and architecture communities what it actually does. So it estimates the speed up of your application for each number of CPUs, but that estimation is an upper bound, meaning that it cannot be better than that. So it's the upper bound of a speed up for your application, given the characteristics of your application. And it's estimate, it's not accurate, as we will see. So here is how Amdahl's law works. So let's say this T1 is the execution time of your application on one CPU. So let's say I only have one CPU and I run my application on this CPU, and this is how long it takes. So if I look at this runtime of my application, at some points in time, it's only one thread is running. Let's say you have a critical section or you have one of those reduces, so it's serialized, right? Only one thread is running. And there are portions of time that you could potentially parallelize your application. You can run multiple threads to speed up your application. So if I look at this, I can divide it to serial portions and parallelizable portions. Now, okay, if I know that, and now I give you 4 processors, for that portion of time that was serial, you still, even if you have 4 processors, it's going to take the same amount of time because it's serialized. So 3 processors are not going to do anything. One of them is going to run, and this is how long it's going to take. Now, for the portion that was parallelizable, now that you have 4 cores, it's going to be shortened by 4. So this is divided by 4. Now I can parallelize. So the time is shortened here. And the same, right? Here, the serial portion doesn't change. The parallelizable portion changes, just divides by the number of CPUs that I give you. So now we can use this to calculate the speed up for X number of CPUs. Your speed up is basically T1, the runtime on one processor divided by runtime on X processor. So T1, we just go with T1, Tx. So if F is basically the parallelizable portion of your processor, so this is a fraction of your processor that is parallelizable, Then 1 minus f is the serial portion, and this serial portion doesn't change. The time is still t1. So for the serial portion, nothing changes. For the parallelizable portion, which is f times t1, you divide that by number of x, number of cores that you have. And now you can just cancel out t1 from the denominator and denominator, and you get this nice formula. Before moving on, I have to say why this is an estimation, and it's not really accurate. And it has so many factors. I'm going to just mention one or two. So one, was this accurate that I said if T1 serializable is this much, it's going to be the same here? Not really, or here. Sometimes your serial portion could increase. You might have more overhead if you're communicating between 4 tasks rather than 1 task. So this serial portion could actually be more or less depending on your software. The other thing that is basically kind of like a estimate and an approximation is about this parallel portion. Let's say I give you thousands of cores. With this model, it means that each one of the threads would take ft1 divided by 1,000, meaning that it's infinitely parallelizable. You can parallelize it as much as you want, as long as you have threads. In reality, you probably have those limited models where adding more cores is not going to help you with your execution time. So there's probably some limit on how much parallelism you have in these parallel portions. So overall, this is just an estimation, and it just gives you an upper bound on how good it could be. And not, first of all, approximation. The second, this is an upper bound. This is the best you can get. Now this is the graph for different number of CPUs. So from 1 to 65, over 65,000 of cores. And this is the speed up from 0 to 20. As you can see, if I give you, let's say, and then different colors are different parallelizable portion or parallel portions. So let's say your applications is 95% parallelizable. That's pretty good, right? Even in that case, the maximum speed up you can get, if I give you 65,000 cores, the maximum speed up is up to 20. So that's pretty daunting here. So it's way different than, you know, linear model, where with linear you would get 65,000x speed up. Amdahl's law tells you that nope, don't take your hopes high. Max you can get is 20. So we're over time, so I'm going to just move on with this. I'm not going to cover it. I would ask you to read this by yourself. It won't show up in the quiz. So the idea is, the question this answers is, okay, what portion of, like, as you can see here, we have different graphs for different parallel portions. Now the question is, me as a programmer, let's say I have a code, do I know what portion of my code is parallelizable? And the answer is, you probably don't. No matter how good of a programmer you are, it's just hard to know what percentage, what portion of your program is parallelizable. So good, that's bad news that you probably don't know even if you're an expert. Good news is actually you can measure it. You can use Amdahl's law, you can inverse it, and then measure your speed up for different x's, for different cores, and then put everything in your formula. So put your measurements here and put x, the number of cores that you checked, and then this formula gives you f. So you have everything, you can calculate f. And this is actually called the Karp-Flatt metric. So we use me and my colleagues, when I was a PhD student, we used this formula for a bunch of at the time, it was the height of big data analytics. It was before the neural networks became a thing. So we actually tested this on bunch of analytic and some machine learning actually applications, and we figured that you actually get pretty good results out of this. You can sort of accurately, with some variance, calculate what portion of your application is parallelizable. And if you know that, then we used it to allocate cores between applications, and we used like priority notion. So our applications had priority. We were thinking about a data center setting, and we had, we used this Karp-Flatt. That paper got a Best Paper award. And I have put a link to that paper. It's a little bit mathematic. If you're interested in those topics, you can definitely take a look. So with that, I end this lecture. I was hoping to be able to talk about real-time systems, but I wasn't. So we'll start talking about real-time systems from next lecture. Thank you for everybody who attended the lecture, and thank you to everybody who is going to watch the lecture. Take care, be safe, talk to you later. Bye-bye.